Let's so today's weekly contest, problem 1, report spam message. We are given message with vector of strings, banned words, also vector of strings. These vector of strings, banned words, if at least two of them is present inside message, then the spam is a message. We have to return if it's a true or not. Then I can just have a unordered set which will be of string type. Uh, Filled with banned words. Then I will have a count variable. I will traverse the array message. If the message S is present inside set, then I will increase the count. If count is greater than 1, then return true. Otherwise, return false. Time complexity will be O of n and space will be O of n. The second problem is very interesting. Minimum number of seconds to make mountain height 0. Well, we are given a mountain height which we need to reduce it to 0, and we have worker times, right? This worker times indicates rate, how fast the worker is. If it's small, then the worker is faster. If it is not small, like 2 is a slower worker than 1. And how it is determined, uh, how many seconds is going to reduce a height by 1, that is determined using this arithmetic formula. At first second it will reduce the height by 1, but it will take this many seconds. Second will be this many seconds. I mean, second iteration of reducing height by 1 will be this many seconds. And similarly, so on and so forth. X here represents the amount of reduction done on the mountain, right? That's what X here means. And this in total is the time taken to reduce the mountain by X height. Right? So this is a problem. We have to determine the minimum number of seconds. Well, it's also given that all the workers work simultaneously at the same time. So, well, there are multiple ways to solve this problem. I'm going to show, I think, two ways to solve this. The first way is if we choose a worker, right, and we have to minimize the time, then I'm going to choose a worker that is faster, right? Suppose I choose 1 because this is a faster worker. So this will reduce mountain height by 1, okay, and it will take 1 second, okay, and then I will push this back inside the worker times, but with increased rate to this much. This will be the new rate of this worker because the worker will get slower with time. So that's how we are going to solve this. Like the intuition here is, we have to get the minimum or the fastest worker at any given point of time, and we'll continue this till mountain height is 0. So I can use a priority queue where min heap to be specific, because I need a faster worker at any point of time. What will be its new rate if I suppose this is the worker, I use it, the new rate will become 1 into 2. I use it, the new rate will become 1 into 3. So at any point I need the original value of the rate for that particular worker and the number of times that worker has been used. And since inside priority queue I need to organize my uh, values in a way that the lowest rate is at the top. So I need the first value to be the rate, the second value can be the number of times or even the original value, and the third will be the remaining, that is the number of times. So my heap will contain three things: the current rate, the original, and the number of usage or number of times used. I'll call it usage. So min heap priority queue. Alright, this will be three values. I can use a tuple, but I'm going to use vector. Uh, since long is going to be used a lot, so let me do this. Vector of vector. This is the min heap. Let me call this PQ. I will initialize PQ with the initial values of original, and one time used. Right, so the priority queue will contain original n, original n, 1. I'll continue my next loop until my mountain height is 0. I will have an answer. I will get the values. Current rate will be this, and this will be 1, this will be 2, original value I'm sorry, original value, usage, and I will pop this. Okay, at this point I will increase my answer. This will be increased by how much? By the current rate. My new rate will be, my current rate will become new with what value? The original value into the number of usage plus 1. So since it's used, this will be the new value, which will be usage plus 1, or instead let me do it this way. Alright, and finally I will push this inside my priority queue, current rate, comma, original, comma, usage. Also my mountain height will get reduced by 1, so that's important. And I guess that's it. I think this might overflow. And by the way, current rate is something that will be large value, so it will be long, and I think all the values will be long, so this is fine. This won't be long, in the sense that these are original and usage, but this one needs to be uh, taken care of. And okay, actually, this answer, I don't need to accumulate it, because all the workers will be working simultaneously, right? So I just need to get the maximum time that any of the worker is taking, and I'm minimizing it based on my minimum heap. Alright, so this is what I have to do, and I guess, yeah, that's it. Let's see if this works. Time complexity will be O of n log n, and space complexity will be O of n. Uh, okay, there's something wrong. Oh, my bad. Current rate needs to be accumulated, right? Because the new rate will be addition. My bad. I didn't show it here. This will be 1 plus whatever the new value is. This will be the old value, that is 3, plus this. So it's going to be this. This should work. Time complexity, like I said, it's O n log n. It's overflowing somewhere 18th line. Yes, this is overflowing. Let's take care of this. Uh, the other way of solving this is using binary search. We can do a binary search on time. What will be the, let me comment it. Let me start fresh. What will be the range of the uh, time on which we can do binary search? So the range will be starting from 1 second, ending at what? Well, since this is the formula, sorry, this is the formula, and we can clearly see that this is a arithmetic formula. If we take worker time of I as common, we get 1, 1 plus 2 plus 3 plus up till x, which is a arithmetic progression. Alright, so which has a formula n into n plus 1 by 2. So here, if I take the worst case, we will get the end for time. If I take mountain as this, and this is what we need to reduce, right? So this is nothing but x here, and what will be the value that I can take common outside? That will be nothing but the worst case for worker time, that is 10 to the power 6. So if I do a arithmetic on x like this will be plus 1, so which will be approximative to this itself, and divide by 2, and the common value is 10 to the power 6, which is nothing but uh, this will turn out to be 10 to the power 10 plus 10 to the power 6, 10 to the power 16 is what it will turn out to be, and uh, this will be our end. This will be our binary search range. Now let me take long values because these are large values we are dealing with. 10 to the power, or let me take this 1e 16. So while start is less than end, then I will get the midpoint will be, since these are large values, I'll get the mid like this so that it doesn't overflow. At this point, I want to check if this is a valid time frame or not. By valid, what do I mean? By valid, I mean that uh, if this mid is nothing but a fixed time which represents maximum possible time that a worker is taking, any one of the worker is taking, right? But I want to, determine if in this maximum possible time, is it even possible to reduce the mountain height by this much amount? That is the case to determine if it's valid or not. If it's valid, suppose this is the function I'm calling to get my answer. I'm passing some variable or arguments. If it is valid, then I am trying to minimize the time, right? So I'll go on the left half. Alright, so let me get the answer, which will be end at this point. I will try to minimize it, so this will be my new answer, and I'll retry by going towards left side, else I will go towards right. Alright, I'll return answer here. Now let's come back. What is valid? Well, is valid is going to determine if it's even possible to reduce the mountain height in this max possible time. So I will pass max possible time. I will pass the mountain height against which we will check if it's valid or not, and will pass the worker times for which we can, let's see what we'll do. We'll have to understand that first. Is valid, uh, this is the max time, this is actually, this is not max possible time here, it's mid, uh, this is the height, and this is the vector of int, I call this weight. Alright, so at this point I'm essentially finding out the height that is possible for a particular worker to reduce in this particular max time, and that height can be anything between 0 to whatever height is given. So I can do another binary search for each worker so that I will get the height, so that I can get the reduction for each worker, and that I can accumulate to find out if that is greater than equal to this height. If it is, then I will return true. If it is not, then I'll return false. So this is a nested binary search concept. Let's see. I will have a total reduction here, which I'll call 0. I will traverse uh, through each worker, and I will call uh, let's see what I'll call total reduction. I will accumulate the reduction for each worker plus equal to, I will call another function at this point where we'll do a binary search on height. So let me call this max reduction for worker. At this point I'll pass n, I will pass max time, and that's it. If at any point in this iteration total reduction gets greater than the height, in that case return true itself here itself, because anything further will even increase the height further, which I don't even care now since it's a valid case. Otherwise return false. Fine. At this point I will call uh, this function where we will do a binary search on height. But since we are going to check, uh, let's see, I'm going to do a binary search on height, right? The start will be 0, the end will be the mountain height itself, right? But I don't have anything to evaluate that, so I pass the height here as well, so that I will have something to have the upper limit for. I will have a answer which will be initially minimum because I'm trying to maximize it. Alright, so while start is less than equal to end, the mid is this start plus end minus start by 2 so that it doesn't overflow. If, or let me get the, now how are we going to calculate the time, right? That's what we are going to compare this against, right? So in this particular time, can we even reduce the height? And if it we can, then for a particular worker, what is that reduction? That can be determined using this formula. So I can just calculate the max possible time for worker. For any worker, this cannot be greater than equal to max time. If it is, then it's a invalid case. Alright. Okay, so n is the common value, that is worker time or the rate, into this is the fixed reduction that we have decided. So this is nothing but x. So mid into mid plus 1 by 2. This is the maximum possible time for this worker. And let me make sure this doesn't overflow. Alright, if this is greater than equal to, or if it's less than equal to max time, then it's good enough. So I'll try to maximize the height. So I'll go over to the right half. Start is equal to mid plus 1. I'll get the answer at this point to be start, or sorry, mid, and otherwise I'll go towards the left half, and finally return answer. Alright, so this is what it is. This is a complicated solution. Let's see if this works. Alright, it's somewhere overflowing. So my bad, I made a mistake here. This should be long, long, and I think this should work. We need to be careful with the overflowing problems. And yeah, it does work. Time complexity will be interesting because we are doing a binary search on time. So this will be O of log max time, and inside for every worker I am doing a binary search on the height, and that is the mountain height. So O of height. Alright, so this is the whole overall time complexity, and space complexity will be O of uh, I guess O of 1. Yeah, O of 1. Alright, so this is what other solution is, but can we do something better? And the answer is yes, we can do, because at this point, this is fine, this binary search is fine on time, but the binary search on height is not really required, because if we try to see what are we trying to find in the binary search, the mid or the reduction, right, which is nothing but x. Alright, but if we try to solve it using maths, that will come out to be, it's nothing but x into x plus 1 by 2. Alright, multiplied by the rate, and this should be less than equal to the max time. So this is the reduction, this is the value, this in total becomes a time, and this should be less than equal to the max time. This will be nothing but a quadratic formula, which if you try to solve it, it will become x uh, less than equal to, suppose max time is m, and this goes here, this goes here, and if I try to uh, make it a perfect square by adding 0.25 on both sides of the expression, and if this is split, this will become nothing but 0.5 whole square, and this will remain same. This will overall become square root of this minus 0.5, and this is what x is, over which we were doing a binary search, but it is not really required. We can just find this x for every worker and accumulate it into the same thing that we were doing here. So I'm not going to show that, but that is better in terms of time complexity, and this will reduce and remove this part. So eventually this will be where overall time complexity and space will be over. Alright, so this is problem number 2.